Hey everybody, the purpose of this video is to hopefully explain to you all why a least squares regression line is called a least squares regression line. So what I've got here is 5 points in the coordinate plane. I put them all in the first quadrant to make them easier to see and tried to use nice coordinates. I'm going to go ahead and turn their labels off just to make it a little bit easier to see what's going to come next. Now if you look at these points and one of the things you should always do with your data is take a look at it. You know, does it look line-ish? Does it look linear? Okay, these 5 points here tend to look left to right as if they're rising. So you might think, okay, I can get extravagant, maybe think it looks cubic or something like that. But you know, probably the simplest model is they look kind of like a line. So the question, of course, is which line is it? Well, here's a line. There's a line. There's a line. And there's a line. There's lots of lines we could potentially put through these points, but the question is which one is a line that describes them the best. And this is part of what your project is all about. So obviously that one is missing them quite a bit, as is that one. So it looks to be maybe something somewhere in here, somewhere, yeah, maybe like that. Okay, so the question is which, because I could then move it a little tiny bit like that and say, oh look, that's pretty good too, as is that, as is that. So we need a measure of how well each of these lines is, if you will, fitting the points. Now what statisticians have come up with is something called a residual. Here are the residuals. So supposing this line right here is fitting your data, these little green lines are showing you how, if you will, off the line is from the data. Some of the residuals are positive. This one down here is negative. Okay. In the ideal world of a best fit line, which we're eventually heading towards, a best fit line, the sum of the residuals is 0. Now you might remember why that is from our talk about standard deviation back in your first stat course. If you talk about the sum of the distances of all the data points in a set from the average of that data set, the sum is 0. So statisticians overcome that in the measure of standard deviation by squaring the differences. And that's exactly what we do here. We're going to take these measures and then we're going to square them. So this is geometrically what that would look like. Take each residual and then square it. Okay? So now you're starting to see why the word squares is in the phrase least squares. The trick is, why is it called least squares? Well, if you measure the areas of all 5 of those squares, this is 1, 2, 3, 4, and 5, just for reference. Here are some areas I've got for those 5 squares right there. And down here is the sum of those areas. Now the units, just so you know, the units on these squares are meaningless. It's just to throw a number out there. There's definitely a unit you want to use when you're measuring this, and the project will discuss that. But now, as you move the line around, you see what happens. The squares, which are a representation of the squared error, change as the line moves. Kind of cool, huh? So you can see the further we get away from the data, the bigger those squares get. So what you want to do is you want to finagle those square areas until you've minimized the error in those squares. So what I'm going to do here is I'm going to throw the equation of this line that I'm messing around with right here. What I want you guys to do is, as I'm finagling, I want you to watch that sum of squares. We can make it very large by making the line extraordinarily ridiculous. Or we can make it smaller as we drag it down like this. So it's getting pretty small, pretty small, pretty small. Let's mess with it a little bit. Oh, wait a minute. Hang on a second. Hang on a second. Look at that. 0.7, 1.1, 0.8, 0.7, 0.6. Okay, getting pretty small, getting pretty small, getting pretty small, getting pretty big again. Now, as it turns, very magical, because I knew the answer in what the best fit line is, and if I get down to it, it's right about there. That line, 0.35x plus 0.55, is the best fit line for these 5 points. Now, as you might guess, doing it this way is not the most sensible way because it requires a lot of guesswork. And obviously, I didn't do it this way to get that equation. I got the equation via the method you're learning in your project. But I just wanted you guys to have an idea of what least squares regression meant. And that's exactly what it means. If you are to drop that best fit line into your data points, it creates the smallest sum of the squared errors. A couple things to note. A couple things to note. This least squares line does not tell you anything about how well it fits the data. You need something called correlation and the R value, and you'll get to that in your project as well if you haven't already. That correlation is a measure of whether or not you should even be using a line to describe your data. And if you should be, actually, I take that back. It doesn't tell you if you should be using a line. It tells you, assuming you should be using a line, how well that line fits your data. Okay? So you have to always, and again, basically you want to look at your data to decide if a line even fits it well. This one looks pretty good to me. Looks like linear data. So basically, your least squares regression line is just that. It's the line through data that generates the least sum of the squared error. So I hope that demystifies it a little for you, and we'll catch you in class.